Hello everybody, and welcome back to another Eng 130 video tutorial. So as I mentioned last week, we covered basically all the concepts of the week, but the problems that I gave you to cover the concepts were the simple ones. They were great to show you kind of the ins and outs of what we're trying to learn and what to do with each method. But now we have to do some examples that more or less apply these methods, because the other examples that we taught were pretty straightforward. But now I'm going to give you some more challenging problems that don't exactly have a solution that's given to you like the other the other examples. The other examples have a very strict procedure. You do this, then you do this, then you do this. But I'm going to give you some problems now that are more wide open, and you have to apply what you know to solve the problem. So they're not just given to you straightforward. For this problem specifically and like the other problems, you can solve it two ways. You can use the parallelogram method, or you can use the Cartesian vector notation method. For this one, I'll show both. But moving forward, I think I'll stick to Cartesian vector notation, because even though I tell you guys, choose what you want, both work, well, they do both work. Cartesian vector notation is a much quicker method, and once you guys pick it up, you'll go through the problem super fast. But it's also very useful for the remainder of the course. The remainder of the course, you can't really use the parallelogram method for most situations, but Cartesian vector notation you'll use till the end of this course. However, you will also use for the rest of your life. And I'm not kidding. I'm a structural engineer, and I use it every day. All right, so without further ado, let's just get on to the example. All right, so looking at the example, it states that two forces act on a screw eye, which we see as F1 and F2. And they give us F1 is 400 newtons and F2 is 600 newtons. And the problem asks us to determine the angle, theta, between 0 and 180 degrees between them, so that the resultant force has a magnitude of Fr equal to 800 newtons. So this problem's a little different than the last ones we solved, because instead of giving us the geometry and having us find the resultant force, they give us the resultant force, and we need to work backwards to find the angle. So as I was saying, this problem can be approached in two ways. First, we can use the parallelogram method, or we can use Cartesian vector notation. Both will give you the exact same answer, so it's really up to you which one you feel more comfortable with. Now, if you were to ask me which one do I choose, it's going to be the Cartesian vector notation. And this problem will be maybe a little misleading with it, because this problem works out really nice for the parallelogram method, as you'll see. And I'm scared a lot of you guys may think, hey, it was pretty quick parallelogram method, I'm going to stick with that because it looks quicker. I'm just going to say that this problem is kind of an exception to the rule. So just because this one may look a little bit easier with the parallelogram method, I wouldn't say the parallelogram method's easier overall. But the reason why I suggest Cartesian vector notation is because you use it for the rest of the course. So if you become really good at it now, you'll become really good at the remaining material for the course, which of course will help you in the end. All right, well, let's start with the problem. So we're going to start off with the parallelogram method. So the first thing I'm going to do for you guys, just so you guys maybe can follow along a bit better, is I'm just going to color code my vectors as always. So let's have F1 as a red vector. So when you see me using red, you guys know it's F1. And F2, let's have that as a blue vector. So if you guys see a blue vector, oh, I clicked eraser. Hold on one second. So if you guys see a blue vector, you guys will know I'm referencing F2. All right, so I'm just gonna go back to the regular one. So we'll go, I'll just call it the para method, but you guys know which one I'm actually doing. Para method. All right, so we recall that with the parallelogram method, if we're adding two vectors together, first we want to create that starting point, that origin, and then we can start placing vectors upon it. So just like I've done before, let's start placing these vectors. So I'll create my origin kind of on this side. I go up, and let's start with F1. So F1's a red vector, and it kind of goes up and to the side. Oops, back to the eraser again. I will figure this out, I promise, guys. All right, so F1, let's just say, looks like this. So we don't know the exact angle, so we can't really know exactly where to place it. But again, it doesn't matter As long as you get the numbers right, the math will work itself out. So that's F1. And let's just label it its value so we know that F1 is 400. So let's just go 400 newtons. Perfect. So the second vector we have is, of course, a blue vector. So I'm going to just go back to the blue, F2, and I'm going to come down, back to the eraser. Sorry, guys. All right, let's just do something like this. Why not? Shade it in, make it nice and pretty. Alrighty, and we, of course, want to put the magnitude on, and we know that F2 is 600 newtons. And then finally, we have the resultant force between them. So as you guys will recall, the resultant force starts at the origin, so this point over here, and it goes to the head of the second placed vector. So it's going to go just like this. F2. FR. And we already know FR, so this is kind of where the problem's different than the other ones. We know FR because they're giving us FR is equal to 800 newtons. Oops, back to the eraser. 800 newtons. All right, so there's our triangle. And typically, we can use this triangle to solve for everything. But as you guys will recall, the next thing I like to do is place the geometry on the triangle. Any angles we know, anything like that. So if we look up, we know that the angle between F1 and F2, this angle right here, this theta value, is what we're trying to solve for. The problem that we have on here is we don't really have that angle. What we could do is we can find the angle here between F1, back to the eraser, the angle between F1 and the horizontal axis, and we can also find the angle between F2 and the horizontal axis, so these two angles right here, and we'll go 1 and 2, and we know that that theta will be both of those added together, but that looks very complex. And in my experience with these type of questions, if you guys were to have one on a midterm or an exam, what you can usually do is place the geometry. So if you have to split it up like that, chances are there may be a bit of a trick that you guys are missing. And that's exactly what happens in this case. So this problem is either really hard or really easy, depending on if you know that trick. And I know you guys think, hey, this may be a little bit cruel, but you guys will soon learn that that's everything in engineering. If you know the simple trick or the hidden trick, then everything's easy. But if you don't know it, it is the hardest problem ever. So the trick in this case is the triangle. So remember that I said in the previous examples that it does not matter which which vector you start with, F1 or F2, you're going to get the same answer. And that's what you have to realize for this one. So we started with F1 and got our triangle this way. However, what we could have done is start with F2. So let's put F2 down right here. So it'll go something like this. We got F2 right there. So I'm going to just label this also as 600 newtons for those that just want to remember the magnitude. And we got F1. And of course, they'll end up in the same spot because it does not matter which vector you start with. They'll give you the same resultant force. And this one is 400 newtons. So instead of a triangle, I kind of have two triangles, or kind of a square-ish. It looks square, but it's not. But the nice thing about this is looking at this geometry now, we can actually place the angle that we want. And we know it's going to be this angle right here. That's our theta. So this is the theta that we want. And we can see that we can solve for theta using by solving for two other angles. So that's going to be this angle, which we'll call theta 1, I guess. And then a second angle, which I'll do in pink, and theta 2. So by looking at the geometry, we know that theta, the theta that we want, is going to be equal to theta 1 plus theta 2. And what's nice about theta 1, theta 2 is they're now an internal angle on this triangle, which is perfect. Because if we have all three magnitudes, we can easily solve for one of those internal angles. The way we did it before, those angles were not internal angles, so it made the problem really complex. But now theta 1 and theta 2 are both internal angles. So when we're solving for an internal angle and we know 3 magnitudes, of course, we're going to go to the cosine law. So I'm going to put cosine law. And just a quick recap, if I have a triangle, which I'll try, I should make it nice, I'm in no rush. If I have a triangle like this, so basically not a right triangle, and we have A, B, and C, all along with internal angles C, A, and B, we know that C squared, so this is the magnitude C, not the angle C, is going to be equal to A squared plus B squared minus 2AB times cosine of internal angle C. And what's nice is because this triangle is basically what we have for these two situations. So if we're trying to solve for, and let's solve for theta 1 first. Why not? So theta 1. If we're trying to solve for theta 1 and we're relating our top triangle to the cosine law triangle I drew below, we know that C, the internal angle, that's our theta 1. That's what we want to solve for. Looking up, we also know that we can put A, B, and C in. So looking at A, it's going to be the 400 newtons. So I'm just going to go 400. We can look and we see that B is going to be 800. And finally, when we look, we can determine that C, our last one, is going to be 600. So I'll put 600. So from here, we could rearrange the equation to solve for that internal angle C. And if we do that, we can find that theta 1, and I'll write the equation too. Theta 1 is going to be, of course, inverse cosine. In the end, we're going to have to inverse it. And I really encourage you guys to do the algebra by yourselves because that is going to be very important throughout your engineering career. If you get good at the algebra, you'll get good at a lot of things. I had a couple of midterms where my only mistake was the algebra, and it was just terrible. And trust me, you don't want to be thinking about that, how bad your algebra was on a third-year midterm. It makes you look pretty silly. But back to the question, we got our theta 1 is equal to the inverse cosine of the C squared up here. So our C squared is going to be 600 squared. 600 squared minus A squared, so minus 400 squared. And then minus that B squared, so minus 800 squared. And it's going to be divided by 2AB. So of course we got 2, and then A is 400, and B is 800. Ta-da! Make it look a little nice. Oh yeah. Perfect. So what we'll end up is theta 1 is going to be equal to 46.6 degrees. Perfect. So now we can solve for theta 2. So I'm just going to put theta 2 here. Theta 2, da-da. And if we look at here, our internal angle for theta 2, of course, is going to be theta 2. And then we got, of course, A, B, and C. So looking at the diagram here, if we look up here, our A will be 600. Our B is going to be 800. Oops, slow down, iPad. 800. And our C is finally just going to be 400. So if you guys compare this with the last one, the only thing you guys notice is that A and C values swap. A is now 600 and C is now 400. So then we can put this into the equation. Theta 2 is going to be equal to the inverse cosine. Cosine to the negative 1. And then all in brackets. And then it's going to be the C squared, so the 400 squared. Oops. Come on. 400 squared minus the A squared, which is going to be 600 squared, minus the B squared, 800 squared, all over 2AB, so 2 times 600 times the 800. And let's finish off the bracket. my division sign. Oops. I guess that one's not going to be too pretty. Alright, and then we can, of course, just throw that all in the calculator to get theta 2 is going to be equal to 28.9 degrees. And then, as I said before, we know that our theta, the theta that we want in the question, the angle between the two vectors, is going to be theta 1 plus theta 2. So it's going to be the 46.6 degrees plus the 28.9 degrees. So our theta in the end, I can just put it down here. So our theta in the end is going to be equal to 75.5 degrees. And his final answer, so we'll throw a nice box over top. There we go. So it looks real nice. So that's the parallelogram method for this question. So if you know the trick where you have to draw both of the geometries, really easy. If you don't know that trick, well, you'd be there for a long time, trust me. So it's about the little trick. But if you know the trick, it's a really easy question, as you guys will see. Now, even though it's easy, I still recommend the Cartesian vector notation, which we'll cover right now. So if you guys were kind of maybe sleeping during the first part, I encourage you guys to wake up, shake it off, and get ready for this, because this right here is a great question, because this type of question I can see on a higher level assignment or even a midterm. So this is a great question to know how to solve this process. So I'm going to put CVN method. CVN method. So before we begin, let's just look at the question. And let's just recall CVN. What do we want to do with that? Well, CVN, we can add vectors together if we find both their x and y components. Now, looking at this question, we're not given an x or y axis. But here's a little trick that I'm kind of introduce you to now. But you guys will see it later, because this is a very important part of the course. And this is actually part of maybe week 2 or week 3. I'm not sure which one right now. Is even though you assume x and y to always be, let's say this, the up and down, x and y, this is how it usually is, and then x and y. The trick is you don't have to always go that way. This is the standard way. It usually makes things the easiest, but you can choose any orientation you want. So that's kind of the trick to this one, is because we don't have an x and y right here. We don't know. So it'd be hard to find the components of F1 because we don't know exactly how far they are in x, how far they are in y. However, we can choose our own axis. So for this question, let's choose our axis to be something like this. And I'll make this really bold. So, maybe not that bold. Let's find out what this looks like. Okay. Pretty bold still, but this will show you. So this is how we're going to define our axis in this one. And I'm going to go back to, hey, is it this one? Oops. No, even that one's still too big. All right, technical difficulties. All right, that looks fine. So we're going to define it like this. And you're going to go, Clayton, why are we doing that? Because usually what happens is when people see an angled axes, they get a little concerned. It looks like it's a lot more work. And most of the time it usually is. Don't get me wrong. But in this case, it'll help us a lot. And the reason why is because let's look at F2 real quick. Oops. Look at F2. The vector F2 is perfectly along that x-axis. So if that's the case, it does not have a vertical component, which is nice. So what I'm going to do is I'm going to redraw this geometry down there using our new axis. So if our new axis is this, so this is our new and x and y, right here, we have our two vectors. Like I said, F2 is going to run perfectly horizontal. So we're going to have F2 that starts here. Oops. Starts at the corner here. And it's going to go like so. Perfect. F2. So again, label it just to make sure you remember. So we already recall F2, 600 newtons. Now we need to place F1, and we know that F1 kind of goes up like this. Or again, we don't know exactly how far up because we don't know theta. Well, I guess we do know theta if we just look up here, but let's pretend we don't want to do this. So that's another thing too. If you're given a question like this in an exam, don't show it both ways. Just do it one way. You guys don't have to put yourself through all that torture. And then we'll just label F1 as 400 newtons. So the next thing, which is really, really, really nice, is we already know that we're trying to find the angle between these two. So we got a theta. And then the last bit of information we're given, which we need to solve this question, is the magnitude of FR. So the length of FR. So I'm going to put it FR, and I'm going to put it in these brackets. And those, well, not brackets, those lines, I guess. And I guess you guys will think it's an absolute value sign, which I guess it kind of is because magnitudes are always positive. But what this means is the magnitude. And it'll become more apparent more in week 2 when we discuss why exactly we use magnitudes. But don't worry about it. It just means that it's the length of the vector. So we know that this one's going to be 800 newtons. So we look at this real quick and we go, okay, we got a couple of vectors we want to add together. We know the final answer, and we got one unknown. So if we can create an equation with that unknown and we know the final answer, we can solve for that unknown. But even if you don't want to think ahead, I encourage thinking ahead. It's usually how you solve the problems quicker. But what I would do if we're doing Cartesian vector notation, we know that the basis of that is trying to find the x and y components. So a good place to start, hey, let's just find the x and y components. So we'll start with F1. Actually, let's go F2 because F2 is nice and easy. So I'm going to go F2. So we know that F2x is 600 newtons. Easy, because it only goes in the horizontal direction. And we know that F2y, again, because it only goes in the horizontal direction, is going to be 0 newtons. So that's easy. So now let's go to F1. So F1 now has some components. So we got F1x is going to be equal to the magnitude. So we got the 400 newtons. So I'm just going to go 400. Actually, I'm going to erase newtons for this math part because a lot of people will start getting confused. It's okay to skip the units until the final answer, as long as your final answer has those units. So this will just make it a little bit nicer. So, and in this case, it's going to be times the cosine of theta, because we know there's going to be that vertical component times cosine. And we got F1y, which is equal to 400 times sine theta. Alrighty, so now that we got the components, the next little thing that we can do is we can add the vectors together to give us the resultant. Because since we're given part of the resultant, the FR is 800 newtons, we're going to have to try and work that way, in that direction. So we know that FRx, so the x component of the resultant force is just going to be F1x plus F2x. So in this case, it's going to be 600 plus the 400 times cosine of theta. And then FRy is going to be equal to, well, F2y is 0, so we don't have to even include that. So this one's just going to be equal to 400 times the sine of theta. Alrighty. So now that we're in an interesting spot right now, because we have the components of FR and we have the magnitude of FR. So now if only there was an equation that relates the two, and sure enough there is. So if you recall, actually I think it was 2 videos back, we know that the magnitude of a force, so this is any force, this isn't just this FR force, the magnitude of a force, so I'll just write this in generic terms, so the magnitude of a force is going to be equal to the square root of its x component squared, so the x squared plus fy squared. And that's true for any force in 2D. Even in 3D, we would just add a plus Fz squared to that to the end of that, and it still works for 3D. And like I said, you don't have to remember this formula. It's true for all cases. So it's really, really nice. And you know what the nice part is right here? If we're looking down the list here, we know the magnitude, we know Fx, and we know Fy. So if we're subbing in values from our specific case, and I'm just going to move the squared over, so we're going to get 800. The magnitude of Fr is 800. And again, I'm going to move the square root to the other side just to kind of save some time. So 800 squared is going to be equal to, we got Fx squared. So Fx is kind of a longer one, so I'm just going to put it in brackets. So it's going to be 600 plus 400 cosine of theta squared. And then, of course, plus Fy squared. So down here, I'm just going to go plus. And this one's a little shorter. It's only 400 times sine of theta squared. So, beautiful. And now comes the only thing that I personally think is going to push students away from this type of question, and that's solving for theta. It looks easy. We got an equation with one unknown. We can solve for theta. That's not a problem. But it's going to get a little bit messy in between. And a lot of students will, well, actually, this brings me to another thing, is a lot of you guys will try and use a computer. I know that the big, beefy graphing calculators from high school can also solve this no problem. And for the labs and online assignments, that's great. Go for it. If it gets too complex, I would just throw it in there myself. I'm not going to try and tell you guys that I would go solving this the long way because I'm lazy. I'm not going to do that if I don't have to. But, and hear me out, I personally recommend you guys solve this by hand. And the reason is because these long algebraic proofs, stuff like that, the solving, it's what the profs love for midterms and finals, unfortunately. And I'm going to tell you guys this, and I want you guys to remember this, that there is a final exam question, which I will cover for my final review for you guys. And it is the longest, most painful solving you'll ever have to do in your life. And it's funny because every year that I TA this course, I have to do it over and over again with so many students. I'm happy to actually just make a video to show everybody at once. But the reason why I hate it so much is because it was actually my final when I took the course however many years ago. So it comes back to haunt me every single year. And so take it from me, learn now. This isn't probably too bad compared to what it could be. And what it could be, I'll show you guys later when we get to the final review. But yeah, take it from me. This is a skill you're going to want to learn, or else it's going to make your life pretty tough later on. All right. So let's get down to the messy part, shall we? So the first thing that I'm going to want to start doing is expanding that right-hand side. So I'm just going to leave the 800 squared by itself for now and just get rid of these, well, I'm going to put them in red so you guys know what I'm talking about. I'm just going to try and get rid of these squared signs over here. So we'll go back to regular color. So if we have 600 times the 400 cosine, we're going to get 240,000, 240,000 times the cosine of theta. And then when we go on the reverse and go 400 times the 600, it's going to be the same answer, so we're just going to go times 2. Now we're going to also have 600 times 600, so that's going to be the 360,000. So this is from the 600 times 600. And then finally, we have the 400 times cosine times itself. So from that right there, we're going to get 160,000. So plus 160,000 times cosine squared of theta. So that's for the first part. So I recommend stopping the video now, try it yourself, make sure you get the same stuff. And then of course in the end we also have another one, which is the 400 sine squared. So it's going to be 160,000 1, 2, 3 times sine squared times theta. So problems I see students usually doing, and by students I'm not meaning you, I mean me as an undergrad student because I was an idiot, is I go 400 times sine squared, 400 times sine all squared. I was just going to put 400 times sine squared of theta. And the reason why I'm laughing is because I did that on one of my midterms, and oh, it was the worst. I think I put pi times pi was 2 pi. Oh, I'll never forget that day. All right, but moving on to here. The next thing I like to do is let's just start grouping some stuff together and throwing stuff to the sides. So just doing a quick look, we can move this, I'm just going to go in red. Let's take this 360,000 and we'll throw it to the other side to the 800 squared. So if we go 800 squared minus 360,000, we're going to get 280,000. 1, 2, 3, 4 is equal to, and then we got the 240,000. So I'll go back to red just so you guys know where I'm looking at. 240,000, and we can multiply that by 2. So going back to here, we can go is equal to 480,000. 0, 1, 2, 3 times cosine of theta. And then finally, we can factor out this 160,000 from the sine and cosine squared. So plus 160,000. 1, 2, 3. And again, we're going to factor it out. So we can have cosine squared theta plus sine. Oh, I'm going to run out of room. Ta-da. So this is kind of the little thing that you guys are going to go, oh my god, I am not a fan of this course anymore. It's this right here. It's a trig proof. So this one's a real easy one. So we know that cosine squared plus sine squared is just going to be equal to 1. So this is an easy one. I actually believe it's on your formula sheet. But if it's not... it's an easy one to remember, but this is what starts scaring students, is having to remember trig proofs. And I promise you that if there is any proofs in this course, they're easy proofs. We're not going to go the cosine 2 theta is equal to blah, 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 blah. It's going to be something like this, or what tangent is equal to. That'll actually be shown in the next example, because without knowing that one, it's actually impossible to solve some questions. But well, we won't get ahead of ourselves, so we're just going to say that's equal to 1. And if that's the case, what we can do then is take this 160,000 and put it to the other side. So 280,000 minus 160,000, we're going to get 120,000 is equal to 480,000 times cosine of theta. So the final thing we can do, we can divide by 480,000 to get cosine theta. And it's actually kind of nice. It's equal to 0.75. So then we can just solve for theta by inverse cosining the 0.75, and we'll get we'll get theta is equal to 75.5 degrees. And then we want to box it up, make it look nice and pretty. Ta-da! Oh my gosh, that is not nice and pretty. Ooh, okay, I'm gonna erase this because this will just make me look like more of a fool, and I've done a lot of that today. So we're gonna just try and narrow the making a fool out of myself down. All right, so if we look up 75.5, 75.5, both methods are completely valid for this, which was expected. I won't lie to you guys. All right, so this concludes this example. This was a good one. This was one that I can see being kind of more challenging, more midterm worthy, although a little secret, I think the midterm will probably be a little harder. Because this question is pretty simplistic once you know what you're doing. But for those of you worried about the midterm, again, I will do midterm reviews with actual midterm questions so you can see the difficulty. They're the best way to practice for the midterm, in my opinion. So, yeah, that'll do it for this example, and I will see you guys in the next one. Thanks.